People want to see it later. Okay, so let's begin with the general structure of exam 2. We'll have 12 to 14 problems from chapter 4 and chapter 5. You're allowed a Desmos matrix and scientific calculator. So I highly recommend that you practice using that. Desmos matrix is allowed. It's recommended that you do practice review, practice using this calculator, so you're well settled with during the exam. Okay. Topics to definitely focus on, like must know, is finding eigenvalue and eigenvectors. Exam is going to be heavy. You'll have plenty of problems. Eigenvalues, eigenvectors, how to diagonalize a matrix, make sure you know when a matrix is diagonalizable, stuff like that. Second thing, know the tests. I will discuss this in detail in a minute, but know this, that you will be asked to apply the subspace test. You know, multiple choice questions, like you will be asked to check if a vector space is a subspace or not. So you must know what is that test. I will review it briefly here. And the basis test, if a set of vectors is a basis or not. We will also discuss problems on this. And when a set of vector is linearly independent. Linearly independent, the steps we have to follow to check. Fifth most important thing that you must know before exam 2 is how to find row space, column space, null space, and the dimensions of each. Just know it's all in my lecture notes. It's all in my review video from the in-person courses. If you want to review that in detail, I have specific videos on solving problems relevant to your exams on YouTube under chapter 4. Chapter 4 videos. You will find many examples of all this. And then we have the change of basis matrix. Change of basis matrix. You will be given an ordered basis B, an ordered basis C. You have to go from B to C. There are formulas that I'll discuss. So these are some topics, let me see, that you must know before exam 2. Okay, solve plenty of problems on this. Subspace test, you have plenty of problems in homework 4.1. And they're all on Edfinity in some shape or form. Okay, so the first thing that I have on the agenda is subspace test. How do we check if a vector space is a subspace or not? Subspace test. Number 1, it must have the 0 vector, right? 0 vector belongs to the vector space. B, it's closed under addition. Under addition, that means if this is the subspace they're talking about, you have a vector here, call it U, and another vector here, V, in your subspace. That means their sum must be in the subspace. So let's call this subspace S. If U is here, V is here, that immediately implies U plus V must be here. Otherwise, it's not a subspace. Last thing, it should be closed under scalar multiplication. Why do we use the word closed? Because we want to prove that this is closed, nothing is going to run out. So, you know, closed under scalar multiplication. Scalar multiplication for any real number or scalar, If U is in the subspace, then C times U must belong to the, this is a symbol for belongs to that I'm highlighting right now. Belongs to the subspace. So if U is there, then any scalar multiple of U must also be there. The dot represents CU. Okay, so this is subspace test. You will not be asked to remember this definition, but keep it in the back of your mind to know what to check for. Questions that you can expect in exams will typically look like this. So you'll be given the form. Think of it like this. You are given a subset. It has vectors of this form, A, B, C, and there is a condition. Only vectors where the product of 3 elements is 0 are allowed to be in the subset. Let's call it S. Okay? So these type of vectors are only allowed. So anything when you multiply gives you 0 are allowed. So let's check if the conditions are satisfied. If 1, 2, 3 are satisfied, then we know that this is a subspace. The set contains the 0 vector. How do you check? Well, what is the 0 vector? I think you all must be aware of it now. All zeros, right? Yes, 0 vector belongs in the subspace because it satisfies the condition. For 0 vector, your A is 0, your B is 0, and your C is also 0. So A times B times C, which will be 0 times 0 times 0, it satisfies, right? Is the set closed under scalar multiplication? Yes. If I have a vector ABC, their product is 0, then if I multiply it by any scalar C, that product CA times CB times, oh, let's just pick a scalar K, right? To not confuse with the third entry of the vector, I pick the scalar K, that product will also be 0. So K times A, K times B, K times C will also be 0. So yes, it is closed under scalar multiplication. Is this set closed under vector addition? How many are in favor? You can raise hand and we'll see. Or if not, can you think of a counterexample? Two vectors such that the product of their entries is 0, but when you add them, the product of the entries is not 0. Can you think of an example? So with a little practice, this will be second nature. If I pick U like this and V with any vector you pick, doesn't matter, right? U and V satisfy the condition right here I'm highlighting. 1 times 2 times 0 gives me 0. This also. But when I do U plus V, I get 1, 1, 2. So U plus V does not satisfy, right? It fails. It failed that subspace test, and that's how you check. So just three simple conditions, and make sure you try a few counter examples before you click on an answer in exam, okay?
Dr. Joshi?
Yeah, question?
I guess that was my struggle is knowing what vector to use as a test.
Look, if it applies, if it's true, then it should be true for any vector you pick. So in that case, you pick X, Y, Z, like random letters. But if it's not true, with a little practice, you will be able to find a counterexample. Like I found a counterexample, right? I picked two vectors, U and V, any numbers really, doesn't matter. You could pick 450 or 079, doesn't matter. You pick two vectors that satisfy the condition that A, B, C is 0, but their sum will not work.
So anything, a 0 plus a non-zero number is going to be non-zero. So that's why it doesn't work.
It doesn't work because if this is my subspace, u plus v cannot be there, right? Because the entries of u plus v are 1, 1, 2, but when I multiply 1, 1, 2, I get 2, which is not 0. So the only vectors are allowed in this house are vectors such as their product of their entries give me 0. That's the condition to be in the set, right?
So it doesn't mean that there's not an addition vector that, it's not that all vectors added will not work. It's just that there's at least
It's just
one
you
that,
found a counter example. Yes. So if it failed, so that's what you have to look for. It will be very obvious that, oh, it failed. If I can think of a vector that would not work for this subspace. And that's the vector. You don't have to show it in the splash paper, but if you can think of it and it doesn't work, then it's not a subspace. You could think of a different vector too. You could think of anything with a 0 in a different place, add them, it will not give 0. Make sense? Let's do one more. I have one more example. Okay, let's take this one now. So now I have a subset. Let's call this the little house S. The only vectors are allowed, the only vectors that are allowed if they satisfy this condition that I'm highlighting right now. If their sum equals to be 1. So that's the condition they have now, okay? Does this set contain 0 vector? Now that's pretty straightforward. 0, 0, if I put it in the set, 0 plus 0 does not equal 1. So this guy is going to get kicked out. It cannot be in the house because it doesn't satisfy the condition. So no. It failed the basic condition, right? Then you could, well, in exam, you will have to answer these two. Hence the exam, you need to check. Is this set closed under scalar multiplication? Now, what does that tell me? That if I have a vector AB belonging in the set, then any scalar multiple of that, so K times AB, will also belong to the set. That means that belonging to the house means it satisfies that condition that we have put in the question. This implies that the sum of that scalar multiple will also be 1. Now, can you think of a counter example that would not make this true? I can think of so many.
zero, 5.
Pick anything, right? Pick any vector, any numbers you pick. Say 1, 0, I pick, and I say 5 is the scalar multiple. I get 5, 0. Well, clearly 5 plus 0 is not 1, right? Although 1, 0 was in the set because 1 plus 0 gives me 1, the scalar multiple is not there. It's not closed, right? Similar example you can pick for vector addition. I could pick 1, 0 and 0, 1. They both belong to the set because they both satisfy the condition that their sum is 1. But when I add them, I don't get the sum equal 1. So clearly this set is not a subspace. So this was a case where, well, I picked both examples where they were not subspace. I guess I ought to give you an example where it is subspace, right? Let's think of this one. I guess I'll have to figure it out. It's not coming to the top of my mind, but I probably will have it. So when you have to prove, well, it's online course, so you don't prove a lot of things. But if you are struggling to find a counter example, it probably means that you have a subspace. So let's see an example from my lecture notes where we do have a subspace on hand and you cannot find a counterexample because you can prove for any random vector. Let's see. Okay. By the way, if you can solve any example from the lecture notes of chapter 4 and 5, you are good. There's nothing on this test that can surprise you. Oh, there you go. So I have an example here, right? Where I pick a subspace W. Condition is you are in the house if W1 plus 2W2 equals 0. And in this case, you will struggle to find a counterexample because it is a subspace, right? And I prove for any random vector that no matter what you pick, it will work. Even for a scalar multiple, it will work. So this is a good example. Mostly it's easy to prove that a subset is not a subspace. It's difficult to prove that it is a subspace. But you can find more examples here. Okay. Well, this is what you expect from the subspace thing. The second thing I want to talk about is the basis test. So let's do a quick revision. Basis of a subspace. Well, before we talk about a basis, we must know what is linearly independent vectors, right? How do you check? Because you will be asked to check. You will be given a set of vectors. Let you have, a bunch of vectors, okay? V1, V2, V3, V4 is a set of vectors. Check if they are linearly independent. Check if the set is linearly independent or not. So must know how to solve problems like this, because that puts the foundation for your basis test. How do you check if a set of vectors is a basis or not? They must be linearly independent. The dimension must be less than the dimension of the vector space. We'll do an example in a minute. How do I check if a set of vectors is linearly independent or not? I find the augmented matrix with 0, right? And I find the RREF using a calculator. You can use your calculator. Don't waste time finding RREF for exam 2, okay? And if I have exactly one solution, exactly one, or you also call it unique solution, then yes, they are linearly independent. That's the only thing you have to memorize. If you have exactly one unique solution for any given set of vectors, yes, they're linearly independent. If not, they're not. That's it. No confusion. And if you can check for this, then you are ready to move on to the next question that I want to ask you here. There. Wait, I had a few subspace. There you go. Expect questions like this in exams. They're taken from your Affinity homeworks, okay? So they're important. So WB the set. The basis test tells me if I have a set of vectors that are linearly independent, and it should span the given vector space. Why are they talking about R cube here? R3, because I have 3 components in my vector. Okay. Now, can anybody tell me what is the dimension of R3? Like the minimum number of vectors you need to span R3. You know, R3 is like, yeah, you need 3 directions, right? There are 3 directions in R3. So the minimum number of vectors you need are 3. because you need a vector along the x-axis. You need, think of it like this, okay? It's in the video somewhere, it's in my video somewhere. This is the background for vector spaces. Look into my chapter 4 videos. So think of it this way. There are 3 directions. I need at least 3 vectors to span it. If I have less than 3, there's no way I'll be able to span R cube, right? So this is a correct answer. W is not a basis because it does not span R cube. Is it linearly dependent though? That's when you check. How do you check? You augment it. 6, -1, 5, augmented with zeros. And if I get one solution, yes, it's linearly independent. But in this case, I will never get one solution. Why? Well, they are linearly independent, right? When I simplify them, when I find the RREF and solve for, let's call this C1, C2, you will have one solution. So this is not true because these vectors are linearly independent. So this is the correct answer. So a little conceptual knowledge is key for this one. So make sure you read through the lines. Any questions with this? Anybody? Okay, let's do one more. One more example here. I have a determine if W is a basis and check the correct answer below. It's either a basis or it's not a basis, and you have to pick the correct option. W is not a basis because it does not span R cube. Is that true? Now you can't immediately know, right? Because it has 3 vectors. So it is not less than the dimension of R cube. Not a basis because it is linearly dependent. Is this linearly dependent?
Yes.
Yes. Who said that? Good job. You don't even have to check because it has a 0 vector, right? You can pick any answer here, and linearly independent means, suppose you have 3 vectors in your set, okay? You find constants C1 times U plus C2 times V plus C3 times W, making them 0, okay? Linearly independent means that all C1, C2, C3 must be 0. There is no other solution. They have to be 0 to make this linear combination 0. If you can find any other solution, they're linearly dependent. As soon as they put a 0 vector right there in the set, immediately know, don't waste any time, they're linearly dependent, because you can pick any constant for the 0 vector, it will work, right? Linearly dependent cannot be a basis. Good, that's the basis test. Let me do another example, which is very important for this exam. I don't have a screenshot, I couldn't find it, but it's in my lecture notes. So, and I don't want to solve a similar problem we did in your Edfinity. So there is a question. Find a basis for the subspace spanned by, find a basis for subspace spanned. I'll post my notes, no need to worry about it, spanned by. So I will be writing a lot, but just follow the process, solve it alongside. There you go. The most math that we'll be doing is finding the RREF, which I will not be doing because you have a calculator now. -4, 2, 3, 1. So this is a question. And I have -2, 3, -4, 3. And then I have -18, 20, -4, 16. Then I have 15, -11, -8, -7. There you go. Okay, so when I say subspace spanned by, that means I'm using now, right now, I'm using all these vectors to span my subspace of dimension 4, because I have 4 entries, right? It's a subspace of R4. And what is the basis of R4? What is the standard basis of R4? Dimension of R4 is 4. Think 4 directions, right? So any set with more than 4 vectors is inefficient. It has something redundant, something that can be a combination of the other 2 vectors, right? Any spanning set containing more than 4 vectors, okay, must be linearly dependent, because it has extra stuff. It is not efficient. So how do we get rid of that extra stuff? Because a basis is the efficient number of vectors. You cannot have extra vectors in there. How do I find a basis? Just remember the steps. I combine all the vectors given to me in a matrix. Okay, I'm going to write it again. -4, 2, 3, 1, -2, 3, -4, 3, -18, 20, -4, 16. I'm just copying down the vectors. -7, and I will find the RREF. That's the best way to weed out all the unnecessary vectors not needed to span the subset. Okay, so RREF, use Desmos calculator. I'm not going to be doing this. I'm going to copy the answer here. 1, 0, 0, 0, and I have 0, 1, 0, 0, 0, 0, 1, 2, 4, 2, 0, -1, -4, 0, 0. So I do the RREF, and then I find the columns with the pivot. So again, how do I find the columns from the pivot? Start from the top left. Top left, I have a 1, go down and right. I got a 1, that's my pivot. Go down and right. I have a 1, that's my pivot. Go down and right, no 1. So I only have 3 columns with a pivot. The columns that correspond to the pivot entries will be my basis. The rest is extra. So basis for the subspace is the columns that have the pivot. So those vectors. So the vector 1, vector 2, vector 3. Okay. And I think I've been reading your messages on it at discussion. You will be given instructions in the exam on how to plug in the basis in Edfinity, if not already done so with the homework. Now, how many vectors in the basis? Only 3. So the dimension is 3. Right? Only 3 vectors are needed to span this subspace, and the 2 are extra. And you could, if you just look a little harder, you'll probably find that these are linear combination of these 3, some linear combination of these 3. You'll be able to find that. Okay, this is one of the important questions. Anybody, any doubts?
Dr. Joshi?
Yeah.
Here. That rule that you wrote up there, would that apply if it was, if there were 4 vectors with a dimension in R3, as long as there's more vectors than the dimension? Or...
They must be linearly dependent. Yes. Yes. Any vector space Rn, if you have n plus 1 vectors, they cannot be a basis because one of them is extra, right?
Okay.
Think of it this way, right? It's like, you're being, somebody's giving you directions, and to get the directions in R3, you only need 3 vectors, right? But somebody's giving you extra stuff, like some vector here, some vector here, some combination here, extras, right? You could use a lot of extra vectors, but you really need only 3. That's how you think about it. Okay? That's the number. Okay, now most important thing about chapter 4, then I'll move on to chapter 5, is the rank and nullity theorem. So I'll solve one question. I have plenty of problems solved on my YouTube channel. Expect a question like that in exam. Now, a lot of work is simplified if you do not waste time on RREF. So this question will cover all about rank, the spaces, the row space, null space, and all that. Nullity, okay? This question covers all. So you will be given, hold on, get my notes up there. So you will be given a matrix sometimes. Sometimes you'll be given the RREF form. That's even better. Suppose you're given this matrix, 5, 4, -2, -2, 15, 12, -6, -6, 5, 4, -2, -2, 0, 5, 0, 1, and then 4, -3, -2, -5. Now let me just quickly recap. I know it will be a lot easier once I solve a problem, but keep these definitions in the back of your mind. What is rank? Rank is a number. It is basically number of non-zero rows in the RR or REF form. Okay? Everybody clear with what is a non-zero row? We'll discuss this in a minute. It's a number, okay? Number of non-zero rows. What else? Nullity. Nullity is nothing but number of columns in your matrix A minus the rank. And this gives rise to the popular rank nullity theorem. If you have been reading my lecture notes from the start, you will know how much I love this theorem, how much I keep coming back to it until the end of this course when I teach it. Nullity is number of columns in A minus the rank. Now we will be focusing on these two things and we'll be solving. It's a very straightforward process. It's nothing is complicated in this, okay? So first thing you have to do to find the row space, column space, and all that is find the RREF. Use a calculator, use Desmos, find the RREF. When you do that, the RREF for this one, sometimes it's given, sometimes it's not. This one is 3, 0, 0, 0, 1, 0, 0. Wait, did I get the wrong RREF? Okay, this is the one. You can double check my work. It's very likely I could be wrong. I make a lot of mistakes. So double check everything. Now, there you go. I want to find the pivots now. Start with the top left. Go down, go right. The next one is there. Go down, go right. The next one is there. Anybody, any trouble with this? Finding pivots in your RREF is key. Moving on. Pivots are, so if you're not clear with this, you ask me. In column 1, 2, 3, 4, and 5. If you don't agree, you ask. This one has a pivot. This one has a pivot. This one has a pivot. Good. That's it. That's all you're supposed to do. Then the row space. Row space is nothing but the non-zero rows of your RREF. So 1, 3, 1, 0, 0, 0, 0, 0, 1, 0, and the last one 0, 0, 0, 0, 1. So how do we memorize it for exam purposes? Row space, write down the non-zero. Now don't worry too much about the orientation of your vectors. If your answers and your values match the correct answer, I'll give you a full point. You know, I give partial credits, so email me. Non-zero rows in RREF. Okay, that's your row space. Column space. You see the columns with the pivot entries? Those 1, 4, 5 columns of the original matrix are your column space. So what are the original matrix? Okay, I don't have it here. There. So the column space will be column 1, which is 5, 4, -2, -2. Column 4, which is 0, 5, 0, 1. And column 5, which is 4, -3, -2, -5. Those are the vectors in the column space basis. There you go. What is the definition? Column space. That's how you remember for exam. Columns in the emphasis on the original matrix, because that's where the students make the most mistakes. Original matrix with pivots in R, R, E, F. Okay? That's how you find the column space. And what is left now? Oh, the most important thing, the rank of your matrix A, that's one way to check your answer in exam, must equal the dimension of row space, which must equal dimension of column space. Otherwise, you're doing something wrong. Okay? And rank was nothing but the number of non-zero vectors, non-zero rows in your RREF, which were 3. So that's one way to check your answer in exam. If they're not matching, you're doing something wrong. Next comes, and the most important thing, nullity. How you find the nullity of a matrix A. This is where the techniques from chapter 1 comes into play. You have to parameterize the solutions. How do I find nullity? It's the number of columns in A minus rank. Number of columns in A is 1, 2, 3, 4, 5. Rank is 3. I should have 2 free variables. That's how you check. Okay, so far, any doubts? Can everybody do this in exam? Okay, so nullity is the last thing that you will need to check. Nullity of A. Well, first find out what is the nullity. It's the rank, it's the number of columns, which is 5, minus the rank, which is 2. That tells me 2 free variables. And if you recall from the first review video, the columns that have the pivot are not free. So the free variables are x2 and x3. That's also an important point that I should make here. Columns in RREF with pivots are not free. Okay, So you know what you do when you make this thing, rearrange it back into a linear system. That's what we're going to do. Wait, let me open my notes. Wait, this is not the same question. Oh, this is the same question. There you go. So I had this matrix RREF. Let's copy it down. 1 3 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0. And just for sake of simplicity, I augment it with zeros. And now this is x1, x2, x3, x4, x5. And I already know that x2 and x3 are free variables. But let's just rewrite it as linear system, because that's going to give me the null space. So x1 plus 3x2 plus x3 equals 0. x4 equals 0 from the second equation. The third non-zero row gives me x5 equals 0. I can simplify this a little bit. This gives me x1 equals negative x3, negative 3x2, right? And I let my parameters x2 to be t, x3 to be s. So I have x1 is negative 3t, negative s, x2 is just t, x3 is just s, and we have done this so many times now, or I hope you have done this so many times because this was in exam 1. And when you rewrite it in vectors, right, so I'm going to take t common. What do I get? Negative 3, 1, 0, 0, 0, right? Plus s common, I've got negative 1, 0, 1, 0, 0. And we knew that we should have 2 vectors in our null space, right? And how many do I have? I only have 2 vectors in my null space. Negative 3, 1, 0, 0, 0, negative 1, 0, 1, 0, 0. So you see, it's nothing new that you're doing. You're just parameterizing the solution set. But you have to memorize this process that, okay, I have to find RREF, then I have to augment it with zeros, then I have to figure out which ones are free, which ones are not free, and the vectors there are my null space. And you can check along the question that, oh, I should have 2 vectors in the null space, otherwise you screwed up somewhere, right? So remember the process. The questions will not be that complicated. Oh, and the last topic that from chapter 4 that is very important that you will see a question in exam is the change of basis, coordinate conversion. Now I have a video on YouTube somewhere which details all about conversion. I have a video that talks about it, why it works, just the basics, nothing extra, no nonsense video is somewhere here. I recommend it. It was suggested by one of my students. What? To record a video on that, to explaining why the basis of conversion and stuff like that works. And I recorded it and it was helpful. So I think it was helpful for my students. I hope it's helpful for you guys. Okay, it's not loading it, but I recommend going through that video. I've named it Introduction to Something. So expect a question of a conversion of basis. So you will be given an ordered basis. For example, this is the example I've picked. I have negative 1, negative 1, negative 3 as a vector in my ordered basis. 1, 2, 3, and then I have negative 2, negative 3, negative 7. That's one of my ordered bases. Then the second ordered basis is negative 1, negative 3, negative 2. I have negative 3, negative 8, negative 3. And then I have 1, 3, 3. That's my second basis. And And sometimes, well, most of the times you'll be given a vector u and standard coordinates. This is all the part of the question, okay? Now you should be able to find a few things with this given information. Part A, at least remember how to find it. If you don't want to go into the theoretical part, must remember the formulas. What are the coordinates of the vector u with respect to ordered basis B? Don't want any theory, multiply. And you can multiply matrices and find inverses of matrices using Desmos. So do that. Plug in, I think you can plug in the whole equation in Desmos now. So it should take you like just the time it takes you to plug in the matrix. That's it. Inverse of B times -2, 0, 0. And whatever that answer is, gonna be your coordinate vector. Same thing, if you were finding the coordinate vector with respect to the basis C, you would do C inverse times the vector U. Same thing, right? What if you were looking for a change of basis matrix? Change of basis matrix B to C. What is the formula? Is just a product. So I explained all this, the background behind it, but I have to cover a lot for the review. So I won't talk about it here. It's C inverse times B. Now be careful, B to C, C to B keeps changing. Okay?
That's where I got confused. Which one to take the inverse of?
Oh yeah, did I switch it? I think so.
I'm not sure because I'm still a little confused on it, so I'm not really sure. But I kept doing the inverse of the wrong matrix, and I kept getting the answer wrong.
Yes, that's why you need to know the background behind it, right? That's why I talk about it. So think of it this way. Let's say my vector u, right, in the standard coordinate can be represented with its coordinated with respect to ordered basis B using this formula, right? And it can be represented with the ordered coordinate C with this formula. So this is nothing but the vector in terms of the ordered vector, ordered spaces B. And this is that. Now, if I want to go from B to C, what do? I multiply both sides. I'm talking about this equation, equation number 1. I multiply both sides by matrix B. So this is what I talk about in my video when I do the introduction part. I hate memorizing formulas. As you can see, I can never get them right. So this is the formula for change from B to C. That's how you get it, right? So yes, I flipped it. Thank you for pointing it out. If you're B to C, like I said, do not memorize if you have to. Like, I'm not going to judge anybody. It's an online exam, so we can't even check the work. So, but that's how you get it. You're going from B to C. I'm going to multiply by B on both sides. I'm going from C to B. It will be the opposite. I'm going to multiply by C on both sides. That's how you get it. There's a detailed explanation in one of my videos. But that makes sense? Don't get confused anymore, okay? You can always do the little drawing on the side. That's key. This is one of the most important topics. You will get a problem, so solve every question on Affinity and make sure you get it right. And solve every question in my lecture notes too, for extra practice. Now, any questions with chapter 4? This is all the important stuff I had for you guys from chapter 4. Now, chapter 5 is all about eigenvalues. Okay, no questions with chapter 4? Moving on. Chapter 5 will be pretty straightforward. If you can find the characteristic polynomial and you can solve a quadratic polynomial, you will not have a difficult question to find the eigenvalues. It will be pretty straightforward. You should be able to factor a quadratic polynomial in the question. If the math looks too tricky in exam, you're doing something wrong. It's not supposed to be tricky. It's supposed to be very straightforward. Now the question I have picked, because I wanted to do the whole concept in one problem, is not so simple, but this is just an example which covers every part of chapter 5. So suppose I'm given this matrix. There are only 3 things they can ask you with this: find the eigenvalues, find the eigenvectors, is A diagonalizable? If diagonalizable, find me a P, find me a D, stuff like that, right? So we'll do all that with this question right here. Okay, how do I find the eigenvalues? I find the characteristic polynomial, which is nothing but the determinant of A minus lambda I. I know some textbooks do this. They're both correct. Okay, I prefer this method. So I'm gonna subtract lambda 1, -1, 1. So subtracting lambda from the diagonal entries, 2 minus lambda. Now this is where the students make the most mistakes while expanding the determinant, right? So make sure you practice enough problems. So I'm going to expand along row 1. Expand along row 1. So if you recall the formula, it's A11 times the minor plus A12 times the minor, A13 times that minor, right? So A11, make sure you use as many brackets as you can, okay? So this will be 2 minus lambda. Because it's 1 plus 1 is 2, I can keep the minor the same sign. You hide that column, hide that row, same thing. Now the middle one will be changed, right? Oh, was it a cofactor? My bad. It's not minor, it's cofactor, right? Wait. Cofactor, it's the same thing. It's just the cofactor makes the middle guy negative because 1 plus 2 is odd. So the middle one, A12 is 1. We already have the negative sign. -1, 2 minus lambda. And then the last one will be positive, but the entry is -1. So nothing can be done here. 2 minus lambda, -1. Right? And this is not a easy polynomial. I don't know why I picked this question. This is by no means you will get this crazy problem in the exam, but this was the example that I liked. So you have 2 minus lambda square, -1, right? Finding the 2 by 2 determinant. 2 by 2 determinant is multiply these two, subtract. Okay, so I have -1, and then I put a big bracket. So brackets are your friend. Do not skip brackets. Okay, and -1, and then I have -1 minus, and then I have minus of 2 minus lambda, right? So the more brackets you use, the less chances of making an error somewhere. 2 minus lambda, and then I will not open this quadratic for very long. You'll see 2 minus 1 is 1, 1 minus lambda, then I have a negative outside. It will be lambda minus 1. Right, and then I have -1, negative becomes positive. So -1 plus 2 minus lambda, right? And you will get partial credit for this. 2 minus lambda. Apply the quadratic here. We'll do that in a bit. Minus 1, lambda 2, and simplify this. So it's just, oh, wait, you see my error? See my mistake? This is exactly why I'm doing it in real time. Don't be me, okay? This -1 was supposed to be in product of this bracket, and I added it there. That makes the question wrong. Careful. To simplify this, 1 minus lambda, change the sign. So you have 2 minus lambda, 2 minus lambda square, -1, negative lambda minus 1 plus lambda cancels out, -2. So this crazy complicated question is taking me 5 minutes, right? So -4 lambda minus 1, and then I have -2. So what do you get? 2 minus lambda, and then I have lambda square minus 4 lambda plus 3 minus 2. Now to find the eigenvalues, this gives me a cubic, right? So that's not fun. Now I don't recommend multiplying it. Let me see what I did. Oh yes, I multiplied it as usual. So when I simplified it, okay, some algebra happened and I simplified it and I got lambda minus 1 square, lambda minus 4. Now don't ask me how. I can explain it if you need me to in a separate video, okay? I want to keep this video short. Now, suppose there's no way you'll get this crazy complicated math in your exam. But if you end up with a characteristic polynomial like this, what are your eigenvalues? Can you tell?
4.
Eigenvalues, now the multiplicity matters, right? 1, somebody said 1, yes. Oh, I have a chat. Okay, so everything is too slow. 114, good job, Jonah. So 1 is with multiplicity 2, and 4 is with multiplicity 1. We leave it, we don't say a 1 on top there. That are the eigenvalues. Now, why the multiplicities are important, you'll see in a bit when we talk about diagonalization. How do I find the eigenvectors? Eigenvectors, sorry, suddenly my screen is a little lagged here. Eigenvectors, I have to find A minus lambda I augmented with a 0 and find the basically null space, right? And I have to do it for both eigenvalues. So I do it for lambda equals 1, and then I do it for lambda equals 4. Now, let's start with my matrix A. Where was matrix A? There you go. Eigenvectors for lambda equals 1. Okay, so I'm going to subtract 1 from the diagonal entry. So I got 1, 1, -1, 1, 1, -1, -1, -1, 1. Find its RREF. That's how I find null space, right? Okay, we had the solutions here. I don't. Okay, I thought I could do it in real time. Okay, who's gonna find me the RREF for this? Because this is gonna take some time. You can use your Desmos calculator for this. I'm just gonna make this row 0, Clearly they're same. I can just add them. And then I can subtract this row. So this will be 1, 0, negative 1, 0. There you go, right? Finding RREF should be straightforward. And when I do the null space, I see 2 0 rows. That means only one pivot, x1, x2, x3, x1 plus x2 negative x3 equals 0. Clearly, x2 is free. Same, x3 is free. x1 is negative t plus s. When I write down the solution in terms of the parameters, x3 equals negative t plus s, t, s, right? So if I take t common, 0, and then if I take s common, I have 1, 0, 1. So the null space is these two vectors, and those are the eigenvectors for lambda equals 1. Now, no technique here is new. This is all that you've been doing from chapter 1 is just combined in one problem. So process and remembering the process matters. Eigenvectors for lambda equals 1, negative 1, 0, 1, 0, 1. Same thing you do for lambda equals 4. For lambda equals 4 now. Okay, let me write down my matrix A minus 4i. So I'm going to subtract. Where is my matrix? I am going to subtract 4 from the diagonal entries of A. So I got negative 2, 1, negative 1, 1, negative 2, negative 1, negative 1, negative 1, negative 2. And again, I find the RREF. And when I have the RREF, I do the same thing. I find the null space, like above. So to find the RREF, who's going to do it? This is not going to be as simple as the last one. Negative 2, 1, negative 1. It will be 0. Adding this, it will be negative 3. This will be negative 3, right? Now I don't want to introduce a fraction here. Okay, let's see your Desmos skills. Anybody has the RREF for me? No.
It's didn't work.
It's all diagonal ones and zeros. So
All diagonal ones. That doesn't sound right. You should have 1 0 row for sure. Okay, what are you missing? This is another thing. If you have an eigenvalue and you're looking for an eigenvector, this eigenvalue had multiplicity 1. It must have a 0 row. If it's not having a 0 row, you did something wrong.
I got the same RREF. I got the identity matrix, the 3x3 identity matrix on Desmos.
On Desmos. Okay, did we get the right A minus 4i then? Did you copy my A minus 4i? Okay, subtract 4 from here. What do you get?
Negative 2.
Negative
1.
2. 1, negative
Oh.
1, negative 1. Did I copy the wrong? Yeah, see?
I think the second row, second column entry is the.
Yes.
That's it's negative 2. Oh, it's a positive 1 there.
Yes. So I copied. See, I'm very confident that I made some mistake in the copying because I know you must have a 0 row, right?
Oh,
so now that's what you should know. Desmos is probably giving you the right RREF, but we copied something wrong down, right? Good thing.
So
That's why we do this review.
So it should be 1, 0, 1, 0, 1, 1, and then a row of zeros.
Perfect. There you go. So immediately I know that I have to find the null space and I have one free variable because these two are pivots. So x1 plus x3 equals 0. x2 plus x3 equals 0. And x3 is the free guy. So x3 is t. So when I write down the null space, I will get in parameter form. It's, wait, why is it not writing? Okay, this is, there you go. Sorry, my is glitching a little bit. Lagging a lot. Okay, almost done here. So we have negative t, and t. When I take the t common, I've got -1, -1, and 1. So that's the eigenvector. And because I have 1, 0 row, I have one vector in my null space. So the eigenvector for lambda equals 4, this is what you plug in. Now, how do I know if a matrix is diagonalizable or not? That's the important part. That's just 2 steps now. A is 3 by 3, right? Number of columns, well, it is every matrix has to be square. Number of eigenvectors of A equals 3, right? Total eigenvectors. I've got 1 for 4 and 2 for 1, which is equal to the size of A, right? Equal to the order of A. Hence, A is diagonalizable. If you have the number of eigenvectors less than the size of A, then you do not have enough eigenvectors to diagonalize the matrix, because the matrix will consist of your eigenvectors. So I'm going to start with the eigenvectors of 1, which is -1, 1, 0, 1, 0, 1, -1, 1, 0, 1, 0, 1, and the last one was -1, -1, 1. Now, if I remember at Finity, at discussion, somebody was asking about, they flipped the P, the D was something, the vectors were flipped, and somebody answered very nicely, 2. Now, here's the concept behind it. You picked lambda equals 1 first, right? So the lambda equals 1 goes first. Then you pick lambda equals 4 as the third column of your P. Lambda equals 4 goes last. That's why your orders are flipped. But it's okay if you see that your columns are a little all over the place, but you have the right columns and the right diagonal matrix, I will give you credit. So email me. But this is why it's happening. You have to pick the associated column with the associated eigenvalue. Okay? No answers are wrong. If you picked your P to be this, -1, 0, 1, 0, 1, then your corresponding diagonal matrix would be 4, 1, 1. This is also correct. It would still make the matrix A diagonalizable. Okay? There are many correct answers for this. It's just how you order your eigenvectors as columns. As one question that I did answer, I posted it on Affinity at discussion, is you might be asked, so I'll just go over it quickly. You might be asked to find a value of k such that your matrix has some specific number of eigenvalues with some specific multiplicity. So this was a little, it's just the roots of a quadratic polynomial, but I think you need a little brush up. So remember this concept. If the discriminant is more than 0, you have distinct roots, equal to 0, repeated root, less than 0, you have no solution. If I want an eigenvalue of multiplicity 2, means I want the same eigenvalue twice. This quadratic has repeated roots. So it's just a connection between two simple concepts. Just thought this is important for the exam. Expect questions like this. Any doubts with this? What else? This is it. This is all you can expect in exam 2. I have nothing else to, so nobody emailed me about any specific problems. If you have any questions, let me know. I can email you back. You have questions?
I just have one quick question. On the previous slide you were on, if you when you get like I kept getting a cubic polynomial that was very complicated, and like I think you said that if that's the case, then you know you've probably done something wrong.
Not for homework, not for homework examples. Homework is a little complicated, more difficult than the exams. But see, there's the hint. I will never recommend to simplify your quadratic. I think that's the mistake I made here. I simplified my quadratic, leave it until the last step. Because if you end up with a cubic, then you have to do the hidden trial method, you know, find a factor, do the long division. That's just messy. Nobody wants that. Oh, wait, I have a question. Yeah.
So out, I was like, this is really taking a long time for.
I know. It won't happen in exam, but practice, okay? Those are important problems. You must know long division for some other course, okay? The only trick I can say is the similar problems you practice, the better you get at it. Just do not factor, do not expand your quadratic until the very end when you're solving a problem like this. Because sometimes it will happen that you'll be able to take the 2 minus lambda common from all the terms, and it becomes very simple. That's the only advice. And there is a question of algebraic and geometric multiplicity. You know, when we talked about the eigenvalues, one had multiplicity 2. These are called the algebraic multiplicity. Come on. Okay. So the algebraic multiplicity are here when you solve the characteristic polynomial. The geometric multiplicity is how many eigenvectors did lambda equals 1 has? 2. So the geometric multiplicity for lambda equals 1 is 2. And that's how they connect. Sometimes they talk like this also. If the algebraic multiplicity matches the geometric multiplicity, then your matrix is diagonalizable. In other words, you should have the same number of eigenvectors as the order of A. Same thing, right? Does this answer your question, Jonah? Any other questions? Yes. Okay, so this is it. All the best, everybody. And I'll see you in the final review.
Thank you, Dr. Joshi.
Yeah, no worries. Take care. Good luck.
Thank you.
You're welcome. Bye.